is time for us to go into chapter 9. And before you watch this video, please make sure that you look at sections 9.1 through 9.3 before watching this video. It'll make the slides just much more familiar to you. So, welcome to elimination reactions. We are leaving the land of nucleophilic substitution, keeping that. I know it was quick and fast and dirty, but now we get to go keep playing and making more new functional groups. So today's class, lecture 21, is going to be an introduction to E2 reactions, a form of elimination. And we'll take a little commercial break sometime throughout this video to show you some really cool chemistry that I just couldn't wait. That's in section 10.3. So please go look at section 10.3 in Hornback as well before you watch this video. Okay? So let's take a look. And again, it's always good to look at the past as we approach the future. So here are 3 different reactions that if I were to ask you before watching this video or reading chapter 9, if you were to predict the products for these 3 reactions, what would you predict? So I'm going to come along and just do them with you. So as I do a process and I look at any of these reactions to predict the products, again, you want to look for those 4 parts of a nucleophilic substitution. And in the reaction, first reaction, we do have a good leaving group. Attached to what kind of carbon? Yes, that's it. Primary aliphatic. And so these are the 2 most important pieces that you have to figure out. You got to have a leaving group, and you got to know what kind of carbon it's attached to. So now our leaving group is attached to a primary aliphatic, which means there's really only one possible nucleophilic substitution reaction that can take place. And it's not SN1. Nope. It's SN2. Okay? So then I want to just make sure I have all the conditions for SN2. So I have an OH minus here. And I want that OH minus. Is this a good nucleophile? This is an awesome nucleophile. It will do a backside attack, SN2 style, and do an inversion on this carbon. But notice this carbon's not chiral, so it doesn't really matter. Do I have to pay attention to the solvent? You know, the solvent is the 4th part of a nucleophilic substitution, but there was a never statement here. Like this primary aliphatic never goes SN1, ever, ever. So solvent really doesn't play much of a role here. I could have water, I could have the most polar protic solvent ever, and it wouldn't matter a bit. Solvent's role is to dissolve everybody. Everybody's got to be swimming in the reaction to bump into each other to make the reaction happen. So this is a beautiful aprotic, less polar solvent. So it also helps just favor SN2 and will make this reaction go faster, but not change the mechanism from one to the other. So my final product will be with the OH attacking here, plus Br minus falls off. Okay? And that's a beautiful reaction. All right? If my writing looks too messy, then let me erase it for a second and just show you I have it all out. Yes, that was a nucleophilic substitution. So we're in good shape. Okay? Let's look at the next one. And again, be systematic in your approach. Always look for the leaving group and what kind of carbon it's attached to. So here we have a bromide attached to what kind of carbon? Oh, yes! You got it! A secondary aliphatic. Cool. All right. Everybody see that? Okay. So, secondary aliphatic, we still have a really strong nucleophile. So with a strong nucleophile, secondary aliphatics could go SN1 or SN2, but I have a good nucleophile. Yes. So this nucleophile is going to make this reaction become SN2, and the products you would expect to form would be the inverted product here. So notice this is a chiral carbon, and you can test me if I'm right or wrong, but you could test to see if it started out R, it should end up S. If it started out S, it should end up R. Okay? So this is why I have wedges and dotted lines on this molecule to help you practice your chirality designation. So this is what we would expect from chapter 8, and life would be all perfect and happy. But there's a reason why I play horror music at the beginning of this video, and the scary, scary elimination is because it doesn't actually happen. I know. Welcome to chapter 9. Welcome to the fact that you put in a really strong base. Which we love to say is a really good nucleophile. But it's also a really strong base. And so what happens in this reaction is we form the elimination product. We actually eliminate a proton and the leaving group, and we don't substitute anything at all. Nothing gets added to the reaction except for a double bond. This is our new reality. And we'll come back in today's video to talk about the mechanism for this reaction and how it occurs and why it occurs. Okay? But I just thought I'd get you ready for, there's a new sheriff in town, and it's called elimination reaction. And do they happen for the third reaction? I have, again, a great leaving group. I have it attached to, what is it? Yes, you got it. Right, a tertiary aliphatic. And therefore, a tertiary aliphatic is another never statement in here. Tertiary aliphatics will never go SN2. Never. So the only nucleophilic substitution reaction this could do would be an SN1 reaction. I still have a strong nucleophile, strong base in this reaction. And so guess what's going to happen? Yep, you guessed it. Elimination again happens. So now our world is not just is the reaction SN1 or SN2, but our world is SN1, SN2, E2, E1, elimination. Yes, this is what makes Orgoland fun. That now I not only can make alcohols, like in the first synthesis step up here, but I can make alkenes, which are very reactive and fun to play with. So your pool of functional groups that you'll be able to synthesize and make is starting to grow. That's a good thing, not a bad thing. A little side note here. No matter how strong the base is, really, a strong non-bulky base, as it says over here. Oh, let me erase this piece, if I can, so you can see it. There we go. A strong non-bulky base, like OH minus, will always do SN2 reactions, so you're in luck. You don't really have to worry about an elimination taking place on a primary aliphatic with OH minus. But the non-bulky part, it's underlined. Yeah, guess what? There's an exception to this rule that we'll see in today's video. Okay? This entire process where we take a alkyl halide, like the Br attached to the R group, an alkyl halide, and remove the Br with a strong base and create an alkene, gets a very fancy long name, dehydrohalogenation. You can now tell all your parents about that. Woo, I learned about dehydrohalogenation. and your online experience will be so much more enriched. Okay. So when we got these elimination reactions, we saw this one here is the second one. And I want to come back to these rate laws that we use for SN1 and SN2, because we saw when we determined the rate law for this first reaction, it actually did depend on the concentration of the base, which is base minus here, over here, base. And it did depend on the concentration of the alkyl halide. Does this look familiar when we're looking at rate laws again? And so, yep, this whole E1, E2 process, hang on tight to this. This is the same idea that SN2 and SN1 are based off of. And it's just by luck that nature has decided to come up with two elimination mechanisms that model the exact same principles as SN1 and SN2. So now we have our E2, and now we have our E1. So tertiary down here must go through some form of E1 mechanism. Okay? So to make sure that we're able to spy elimination reactions, now our brain is not just looking at good nucleophiles, but not every good nucleophile that's charged is a strong base. So we'll come back and I'll emphasize that in a summary slide, that there are some good nucleophiles that are charged, but are not strong bases. Okay? So here is a bunch of our more notorious strong bases, plus a couple new ones that I want to introduce to you. So you're familiar with sodium hydroxide and potassium hydroxide. And on any problem where we give you NaOH or KOH, what we really mean is that this molecule disassociates, and you guys really want to just focus on the OH minus, and that the Na plus and K plus are called spectator ions. So don't let these spectator ions confuse you. We just can't grab a bottle of OH minus and throw it into a pot and have a reaction go. So what we do is we look on our shelves. Oh, there's a bottle of KOH. I'm going to go grab that bottle of KOH and use that as my source of OH minus. Okay? So these strong bases, O minuses, N minuses, typically go SN2 on any unhindered primary carbons. And basically a primary carbon, primary aliphatic is what I'm emphasizing here. Primary aliphatics are always unhindered because they're primary. Okay? What's going on with these sterically hindered bulky bases? Well, they play a cool role in that these bulky bases actually might not do SN2 on a primary aliphatic. They're so big that they can't even do a nucleophilic addition. They can't substitute. They can't get at the electrophile. So what happens with these big bases? They do E2. E2 on primary aliphatics. Oops, sorry. Oh, you're getting a good view of my head. And so these are two. Potassium tert butoxide, or otherwise known as T-butoxide, is generally our poster child. And this is the one that I use in anytime I want to use a bulky base and I want to do an elimination reaction on a primary carbon. I'll grab this and put it down on paper. I don't have to look on my shelves for it because I can write it on paper. If I don't have it in lab, if I have no potassium T-butoxide in lab, maybe I'll look around and I'll go over to the biochemistry labs because they use LDA a lot, lithium diisopropylamide. This is a common base that's used in biological systems. So I usually head over to the biochem labs if I can't find my T-butoxide. And then you can see this is another big bulky base with these two big isopropyl groups hanging off of them. And therefore it will also do E2 on a primary aliphatic. So again, you have two possibilities. This is similar to having a tosylate and a mesylate. They both do exactly the same thing. I just wrote them down in case I don't have one in lab, I can use the other. Okay? So, oh, let's take a little commercial break, as I mentioned.
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium, uranium, europium, zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium. There's yttrium, ytterbium, actinium, rubidium, and boron, gadolinium, niobium, iridium, and strontium, and silicon, and silver, and samarium, and bismuth, bromine, lithium, beryllium, and barium. There's holmium and helium and hafnium and erbium and phosphorus and francium and fluorine and terbium and manganese and mercury, molybdenum, magnesium, dysprosium and scandium and cerium and cesium and lead, praseodymium and platinum, plutonium, palladium, promethium, potassium, polonium and tantalum, technetium, titanium, tellurium and cadmium and calcium and chromium and curium. There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.
Sodium metal is very, very reactive. It loves being Na+. It can't wait to lose an electron that it actually produces H2 gas, which catches on fire in this exothermic reaction and explodes. But in that beaker of ethanol, there is now ethoxide ions. I have my ethoxide. I have my strong base. I now have something that can go do an SN2 reaction on a primary aliphatic or an elimination reaction. So this is a really cool way of you creating your very own alkoxides to use as either strong bases in a nucleophilic primary aliphatic situation or to use as strong bases in an elimination reaction. Side note, MIT is notorious on April Fool's Day for throwing big chunks of sodium metal in the Charles River. Boom! Or in high school, it has been known to have been thrown into toilets and cause toilets to explode. So I'm only saying this not to encourage anybody to do these things. It's already out there on the web. You can search for sodium metal reactions of huge chunks and watch much bigger explosions than the one I just showed you. But chemistry aside, all cool explosions aside, this is a great way to make yourself an alkoxide that you can use in any of your elimination reactions. Now let's get to the details. What are the nitty-gritty details? And one thing you might want to do is build a model of 2-bromo-2-methylpropane with your model kits, because we'll be looking at that shortly. Okay? And maybe using it to help explain what's going on here. So let's take a look at the details. How do I make an alkene through using this ethoxide ion? And in this situation, notice I've used and started with a tertiary tertiary alkyl bromide, tertiary aliphatic, excuse me, first and last name, which in normal situations, meaning before chapter 9, you would have expected it to go SN1. Okay? But what happens is this strong base comes along and grabs what is known as a beta proton. So let's be really clear. What's a beta proton? Well, the leaving group here is attached to an alpha carbon is what we call it, the first carbon. Leaving group attached to the first carbon. And then, therefore, what I want to look is one carbon away. That would be known as the beta carbon. And this molecule has 3 beta carbons. I'm just pointing out one for this example. Any one of the 3 beta carbons has a hydrogen attached to it. And any one of those hydrogens on those 3 beta carbons, like this one, can get abstracted. As the strong base comes in, it doesn't have to fight its way into the tertiary carbon and try to do a substitution. It will bump into one of these beta carbon hydrogens and pull it off. And that beta hydrogen gets yanked off. What happens to the pair of electrons? Well, they have to go somewhere, so they will fold in and create a double bond. And then the bromide will leave. This looks like a very concerted reaction, everything happening all at once. I need both of these, all the base and the alkyl halide. So again, keep in mind, this is modeling the mechanism of an SN2 reaction. I need both the alkyl halide and the strong base to do the mechanism all at once. And it happens all at once to do this crazy intermediate where they're starting to pull the beta hydrogen off, starting to form the new double bond, and the leaving group's starting to break off. So this would be the transition state and the highest point of, say, I don't have the British Guys movie here. But if I did have the British Guys movie, it would be like, this would be that point way at the top. Then it would fall to create our final products. But notice the key here is that there's a little bit of stereochemical stuff going on here. Notice this is kind of straight away. The proton is straight opposite, anti, from the leaving group. That I'm not trying to abstract a proton from the same side as the leaving group. Sound familiar? It's kind of SN2-like, right? Cool. Let's get into the real details as to why that actually has to happen. Okay? So here's the fine print. There are 2 possible geometries for this elimination reaction to take place. Okay? The base in these images must be bulky. Why is that? Well, if you look at my example now, I have the leaving group here. This is the leaving group. Is attached to what kind of carbon? Yes, right. A primary aliphatic carbon. And therefore, this B minus coming in my example can't be just any OH minus, because OH minus would do a nucleophilic attack. This has to be a big, bulky base. My favorite. Oops, let's make it O minus. Erase that. This has to be an O minus attached to some big T butoxide. CH3, CH3, CH3. So this has to be a big, bulky base that doesn't want to fight its way into the primary aliphatic carbon. And what it will do is it will come and find the beta hydrogen. But what I want you to notice is to make an alkene, just back in the old days. Wait, hold on. I got it. Just a sec. Remember this? Way back when we were doing rotation of an alkene, that they didn't rotate freely. Alkenes are made from 2 p orbitals. And these p orbitals need to be parallel to each other, right? To overlap and create a double bond. So, if you're trying to do an elimination reaction by E2, the whole molecule has to set itself up so that the 2 p orbitals are not orthogonal to each other. The one for the leaving group and the one that has the beta hydrogen, they can't be in this orientation because then there'll be no double bond formed. So the whole anti thing is I need, say, the beta hydrogen here, and I need the leaving group here, so that when this gets pulled off, this pair of electrons can fold in and kick off the Br minus or leaving group or whatever it may be. I need them to be in a coplanar fashion. And when that's the case, you have two possibilities. You can have them, the leaving group up here and the beta hydrogen here. This is the bottom of the two examples I have on the slide here. Or I could have the leaving group and beta hydrogen on opposite sides. Remember on the last slide I mentioned the word anti to each other. These two should be or could be anti to each other. And I would create the alkene on the top. Okay? So these are two possible ways that you could have a double bond form, but what this slide is really all about is making sure you guys understand that I need two parallel p orbitals. So I need a specific orientation of my beta hydrogen, has to be in a specific alignment with the leaving group, hydrogen, leaving group, all in the same plane. Hydrogen, leaving group, all in the same plane. So that when they fall off, I have a double bond. Okay? Cool. So, to emphasize the fine print, the beta proton in the leaving group must be coplanar. You'll also hear in the textbook words like periplanar. These both mean the same thing. They have to be the p orbitals, these bonds from the hydrogen in the leaving group. Have I emphasized this enough? Probably. Okay, have to be coplanar. So, take a second. I'll take a second. Pause. Tell me what you think the correct answer to this clicker question is. And then we'll go over it right now, because I can hear you. Sort of. You can also pause the video. Oh yeah, just pause the video right now. Think about it. When you're ready to hear the answer, unpause the video and I'll start. Three, two, one. Here we go. The answer. Again, I want to start here with this is a secondary aliphatic. With a leaving group of I attached to it, so this is a good leaving group. I now look at my nucleophile slash base, because again, the world could still be, is this a nucleophilic substitution, or is this an elimination reaction? This O minus means it is a very strong base. This will favor E2 on everything other than a primary aliphatic carbon. Okay? So this is going to be an E2 reaction. And therefore, I want to look at the beta hydrogens. Where are all the beta hydrogens attached to my alpha carbon? So then draw them out. Here is a hydrogen, hydrogen, hydrogen. These are all beta hydrogens. And notice, oops, let me erase my secondary aliphatic name here. Notice these are beta hydrogens. So be careful. Don't just look for the first beta hydrogen. Look around and see how many beta hydrogens you have. Because the answer to this question is really there are multiple correct answers. This base could come abstract this beta hydrogen, or it could abstract the other beta hydrogen. And therefore, when these two beta hydrogens are removed, their electrons in their bond will fold in. So this is process one. This is process 2, you have 2 possible reactions that could take place. Okay? Oh, wait. Look who came to visit me, Luna. It's probably a good time for a Luna break because this E2 has been very difficult so far. Say hi, Luna. Hi, everybody. All right. So I can get 2 possible products. So if I do reaction 1 and pull off the beta proton from 1, then I will get B comes from reaction number 1. If I abstract the proton that's on the outside, beta 2, then I will get C. Okay? And we'll see in a video soon, one of these 2 is favored, one is more likely to occur, and would be the only product I would want you to write for this reaction. But we haven't learned that yet, so right now, both of these are acceptable answers. Okay? Cool. So, how are some familiar sites? Hopefully they're familiar sites. These are practice problems that I'd like you to try. Please propose an efficient synthetic pathway of the following conversion. Notice I'm not telling you that it's an SN1 or an SN2 or an E1 or an E2. This is our goal, is I'd like you to be able to show me how to start with one molecule, like this alkyl bromide, and end up with this ether. Now this should look familiar. There's a problem very similar to it on our homework that was due in class this week. Okay? Give this one a try, practice it, and then come back to our Zoom class meetings and let me know, or post your answer to me. Send me your answers by email. Please, I don't care if you email me all the time with tons of possible answers to all of these, because I'm not going to actually show the answers to these unless somebody asks me for them in a Zoom meeting or in an email.